Hello students, let's begin lesson 10. Lesson 10 is a continuation of lesson 9, so let's begin with a review. Previously in lesson 9, we studied two types of estimations: point estimation and interval estimation. Point estimation is simpler one because we have just one number, a single number that explains the population parameter the best, or as our textbook author called, the most sensible value or the most suitable statistic, whatever they mean. Now, the point estimation works well for a simple random sample. And the reason is because of this, the law of large numbers. In case of simple random sample, the population mean can be approximated through the sample mean, and the population variance can be approximated through the sample variance. As a matter of fact, these approximations are actually a limit, like this. The probability, the limit of the probability that the sample mean and population mean are close nearby within a certain bound is going to 1 as sample size gets large. Or on the other viewpoint, the probability that the population mean and sample mean stay far away is going down to 0 as sample size gets large. Similar thing applies for variances, and those are for simple random samples. What is simple random sample, by the way? It's basically selecting a sample, do the process of doing the same thing over and over again independently, exactly like selecting several balls from an urn. With replacements, excuse me. Without replacement, that's a completely different story. With replacement, then everything is independent. And a little bit more precise term for this is independent and identical distributed, because we're doing the same thing over and over again, selecting balls from an urn independently with replacement. Of course, if this the pool is really large, then with replacement versus without replacement will not make too much difference. So we make appropriate approximation anyway, and that's okay because in statistics nothing is considered accurate. So some approximation, some reasonable approximation is okay in any cases. But still, our entire theory is based upon IID. Independent and identically distributed random variables, the collection of which we call the simple random sample. In case of simple random sample, we have these relations. The expected value of the sum is sum of the expected values, and also variance of the sum is the sum of the variances. These two are difficult to prove. They require multivariable calculus. It is discussed in chapter 5 of our textbook, but not in detail. We're going to skip those. And then from here, dividing by n, we can get this. And also from here, dividing by n, we're going to get that. These two we already did. We did in lesson 5 and 6, and also in 7, I think. Anyway, remember mu and sigma squared over n. Mu, population mean, and sigma squared over n. So sigma is population standard deviation. So sigma squared over n. Taking the square root, we are going to get sigma over the square root of n. Okay, so much for point estimation. Now, what about interval estimation? The concept here is sampling distribution of sample means. If you consider a sample and then get a mean and just a single number, that's just a point estimate. You don't have any distribution there. You can still consider probability distribution, but then again, with just one sample, you don't see anything. You need many of those samples. Then you're going to see how those probability distribution is formed. But then again, that can be a little bit confusing because one sample is already a repetition, and in many samples, that is repetition of repetition. That can be a bit confusing, but in any case, that's the idea behind sampling distribution of sample means. We went through some visualizations as well Let's see. Remember these pictures for sum and means. And if we increase repetition, then things are getting more normal. Again, we start from something weird, but increasing more repetition, getting more and more normal. And that is quantified by the central limit theorem. Did you notice that the sum and mean are getting more and more normal as we increase the repetition? Indeed. Indeed. A simple random sample, the sampling distribution of sample means of a simple random sample can be approximated by the normal distribution of population mean mu and the new standard deviation of sigma over square root of n, where sigma is the original population standard deviation. So basically, whatever the starting random variable we have, if you take the simple random sample and take the sample mean, then that follows more or less the normal distribution, as far as the sample size is large enough. Okay, so for large sample size, typically 30 or larger, as our textbook says, but nowadays with better computing power, expectations are a bit higher. So in this class, n is 100 or higher, then I'll assume, okay, sufficiently large sample size, so we'll approximate with normal without much trouble. Less than 50, we'll try to find something else. Between 50 and 100, some gray area. In any case, the central limit theorem says sample mean will follow the normal distribution, more or less. Now, any normal distribution can be standardized through this formula, right? X minus mu over sigma, but instead of sigma, we need nu sigma. That is standard deviation of the sampling distribution of sample means. Oh, wow, that's too complicated. Standard deviation of the original population, sigma, versus the standard deviation of sampling distribution of sample means of a simple random sample. Oh, too complicated. So people created another name, the standard error. And the formula is adjusted now like this. X minus mu over SE. All right? X minus mu over SE, and SE is sigma over square root of n. If you do that, then you're going to get the standard normal. The normal distribution with mean 0 and variance 1. And consequently, you can use the standard normal table. We have done this before many times. For example, here's a visualization. You can start from anywhere. This is a discrete random variable, so it's no way close to normal, as you can see. This is dot plot of the probability mass function, and this is probability histogram. No way close to normal, but if you take sampling distribution of sample means, as you can see, it follows normal, more or less. See? Running again. If we increase the repetition, it'll become even more normal. See? That's a visualization of the central limit theorem. In any case, why is normal distribution so important? That's because of the central limit theorem, the fundamental theorem of statistics. So, no matter which random variable we start off with, so original population distribution can be weird. As weird as this, or even worse. Yet, if you take the sample mean of a simple random sample, then that pretty much follows a normal distribution for sufficiently large sample size. So we can use normal distribution and standard normal table, and we can do all kind of computations. That was the theoretical background. And what kind of computations did he do? Well, we studied finding confidence intervals. What is a confidence interval? Here's the best point estimate, x bar, the sample mean, and then we get appropriate margin of error and get an interval plus or minus margin of error. Margin of error here is z times SC, will turn out. And then there is a certain chance, in this case 95% of chance, that my interval estimation is correct. So the real population mean will fall in this interval, highlighted in blue. And of course 95% of chance that I'm right, so the other 5% of chance I'm wrong. So real mean is too low here, 2.5%, or too high, 2.5% here, because of the symmetry. This kind of thing is called confidence interval. We discussed how to find and do all those computations. Also, we can do it to only one side, and that's called confidence bound. For example, if you're interested in the structural integrity of a certain building or bridge or any infrastructure, then if it is too low, that's going to be a problem. But if it is exceptionally strong, no problem there. And also, if you're considering some amount of some pollutant or something in your aquifer or something, too much is a problem, but exceptionally clean, too less, is not a problem. So in that case, we look at only one side, and the confidence interval consequently is unbounded from here to positive infinity, or from here to negative infinity, like that. And this kind of thing is called confidence bound. So there's a bit of a difference between confidence interval and confidence bound. And as for calculating those technically, we went through those already. And finally, we talked about the idea of margin of error. You see, as you can see from this picture, if I'm right, if my interval estimation is right, then real mean is in blue region. So what is the biggest error that I'm going to get from this best point estimate? The distance from here, x bar, to the endpoint. So that's z times SC. Now, if it is farther away, then the real value falls in the red region, and my interval estimation is no longer correct, so that's out of the picture. Again, for one-sided case, again, the distance from the x bar to the endpoint, the confidence bound here. And if I fall into red region, then my interval estimation is no longer correct, so that's out of the picture. So this endpoint is the biggest error I can get, provided that my interval estimation is correct. So that turns out to be z times SC, or z times sigma over square root of n. And if I know this value, and if I know sigma value, we can calculate n value as well. We went through those kind of examples too. All right, so much for the reviews on lesson 9. And we have some new topics here, and they're going to be discussed in separate videos. Stay tuned.